Okay, so here we are for part 3 of the simplex method section, and we got Carla here. Carla makes 3 items in her pottery shop: large bowls, small bowls, and pots for plants. A large bowl requires 3 pounds of clay and 6 ounces of glaze. A small bowl is 2 and 6. A pot requires 4 pounds of clay and 2 ounces of glaze. She must use up 72 pounds of old clay and 108 ounces of old glaze. She can order more if necessary. If Carla can make a large pot in 5 hours and a small pot in 6 hours, a small bowl in 6 hours, and a pot in 4 hours, how many of each should she make to minimize? Minimize. This is no longer going to be a standard problem. So we're going to have to take a look at, can we use the simplex method if we have a non-standard problem? So I'm just going to go ahead and start laying this thing out, and then we'll figure it out from there. It looks to me like there are 3 unknowns. Our unknowns are going to be x sub 1, x sub 2, and x sub 3. X sub 1 is going to be the number of, I'm going to call them the large bowls. Let's do it in order. X2 will be the number of small bowls. And X3 will be the number of, is it pots? Yeah, pots for plants. We have an objective, but it's different. It's now a minimize problem. So we're going to minimize the time that she spends. Okay. Our objective function, Z, is going to be 5 hours for every large bowl plus 6 hours for every small bowl plus 4 hours for every pot. We do have some constraints. It looks like our limitations are the clay and the glaze. And so the 3 pounds of clay for the large bowls, plus the 2 pounds of clay for the small bowls, plus the 4 pounds of clay for the pots, and she must use up 72 pounds of old clay, so we want to use greater than or equal to 72 pounds. We also have a constraint that deals with glaze, kind of the same idea that we have to use up a bunch of it. It's going to take 6 ounces for every large bowl, 6 ounces for every small bowl. That's interesting, but okay, I don't know anything about pots. I guess they could both be 6. And 2 ounces for every pot. And we want to use up 108. We can get more, but we have to use a minimum of this. And of course, this makes sense here. X sub 1, X sub 2, and X sub 3 all must be greater than or equal to 0. Now, if we were doing this by hand, this would be referred to as a non-standard simplex problem. And what we would have to do is we would have to create a matrix and then find the transpose of that matrix and do these other things to that matrix so we could turn a minimization problem into a maximization problem. And it's going to include a whole bunch of steps that I don't want to do. So I'm just going to use the website again, because luckily for me, it doesn't matter. Now, one thing that might be an issue is in some of the homework problems, because this is a minimization problem, they might not use the letter Z, they might use the letter W, because W is traditionally used with minimization problems. It really doesn't matter. It's just the value of the objective function. Whether you call it Z or W doesn't matter. All right, so let's go ahead and take this thing and put it into the spread, or into the website, and see what's going to happen here. Okay. All right, so I have 3 decision variables. I have 2 constraints. Okay. Here's where things get different. I've got to make sure I change some stuff here. I want to minimize it. I want to minimize how long it's going to take, and I believe that my objective function was 5, 6, 4. So the 5, 6, 4. And my constraints were I was going to use up all the clay. So the clay was, I think, 3, 2, 4, 72. 3, 2, 4, but I want to change this to make it greater than or equal to that 72. So I'm making a change. I'm changing this to minimize. I'm changing this to greater than or equal to 6, 6, 2, 108. I want to go back and check to make sure. 662 108. Yep. And so there's my minimization non-standard simplex problem. Okay. It turns a minimization problem into a maximization problem by rewriting things and multiplying by negatives and all that. Okay. Really doesn't matter what it's doing it for us, and it comes up with this is our solution. We have 104 for our objective function, 1606 for our variables. So from our side of things, 16 x sub 2 0 x sub 3 6 z equals it. Was it 104? I want to go back and check. Yeah, 104. So from our side of things, the non-standard problems look the same as the standard problems because somebody else is doing the work. The big part for us is making sure we write these up correctly and then correctly select the proper function to do. All right, I got a solution, but I need to wrap it up and make it look pretty. Carla should make what should she make? She should make 16 large bowls, 0 small WLS. That's really a horrible bowls. Small bowls. 6 pots for a minimum time of 104 hours spent. Let's call it at work. Okay. So simplex method. The behind the scenes, the math for a non-standard problem, much more than for a standard problem. But for us, it's just a matter of making sure we're clicking the right pieces and parts. All right, last one, blending seed. Top grade turf lawn seed mixture contains 3 types of seed, bluegrass, rye, and Bermuda. The cost per pound of the 3 types of seed are 16, 14, and 12 cents respectively. In each batch, there must be at least 25% bluegrass seed, and the amount of Bermuda must be no more than 2/3 the amount of rye. To fill current orders, the company must make at least 6,000 pounds of the mixture. How much of each kind of seed should be used to minimize costs? Okay. I heard 3 variables, so we'll start there. x1, x2, x3. x1, x2, x3. x1 is going to be, what are these things measured in? Pounds? Pounds. Pounds of, and I'll make it bluegrass. x2 will be pounds of rye. And x3 will be pounds of Bermuda. I have an objective. My objective function is to minimize, again, so another non-standard one, minimize cost. So I'll write an objective function, z equals, my objective function is going to be, what is it? 16x1 plus 14x2 plus 12x3, and I'm remembering, by writing it like this, the answer that I get for z is going to be measured in pennies. Right? If I want to write it in dollars, I got to put the decimal point in there, and it really doesn't matter which way we do it. The answer will be the same. I just got to remember how I did it so that when I get there, it's the right way. Okay, constraints. Oh boy, oh boy, oh boy. I'm not certain. In each batch, there must be at least 25% bluegrass seed. The amount of Bermuda must be no more than 2/3 the amount of rye. and they must make at least 6,000 pounds of the mixture. Well, I'm lazy, so I'm going to do the easy one first. The amount of the mixture must be at least 6,000, so greater than or equal to. Okay. In each batch, I think I got an idea what this is. There must be at least 25% bluegrass seed. In each batch, there must be at least 25% bluegrass seed. So the bluegrass seed must be at least 25% of the total batch. Right. I'm just going to stop there for a second and make sure we're okay with this. We're going to talk about this again. That's the 25%, right? This is the total amount that we're going to make. And so 25% of that, the bluegrass must be at least. At least means greater than or equal to. Right? Now let's take a look at that weird third statement. This idea that the amount of Bermuda must be no more than 2/3 the amount of rye. The amount of Bermuda must be no more than, less than or equal to, 2/3 the amount of rye. Okay. I think we got it figured out. And then of course x1, x2, and x3 must all be greater or equal to 0. Now as it sits right now, this isn't going to work for me because I need to write these as inequalities that I can actually put into the system. Now the first one's fine. x1, x1 plus x2 plus x3 is greater than or equal to 6,000. I can do that. The second one, I'm going to have to distribute and then move all the terms to one side or the other. I'm just going to move them all to the, I don't know, I'll move this one to the right. And so that's going to give me negative 0.75x1 plus 0.25x2 plus 0.25x3 needs to be less than or equal to 0. Okay. And then the last one, I'm going to take this and move it over to the left, and that's going to give me x1 minus 2/3 x2 must be less than or equal to 0. Now, this is even nastier because in a traditional problem, a traditional simplex problem, having mixed matched inequalities like that is really not good. But that's okay though, because we're letting somebody else do the work. So I'm going to go ahead and toss this into the web page. Let's go back over there. I'm going to click Start to restart it. There are 3 variables and there are 3 constraints. My job is to minimize the cost. Let's see. I've forgotten already. 16, 14, 12. 16, 14, 12. I'm doing it in pennies. My first inequality was 1, 1, 1, and they must make at least 6,000 pounds of this stuff, right? My second inequality, that was this one. Negative 0.75, 0.25, 0.25 less than or equal to 0. Negative 0.75, 0.25, 0.25, and less than or equal to 0. And then my third inequality, 1, negative 2/3, 0, and I think it was less than or equal to, I want to make sure, less than or equal to 0. Then I'll click continue. It turns this mixed minimization problem into a maximization problem to give me a direct solution. 1500, 2250, 2250. So so my solution is that x1 is 1500, x2 is 2250. Am I getting those right? Yeah. And x3 is 2250, and then my z was 82,500. 82,500, but remember those were pennies, so that means move it over to $825. So then I'll wrap it up and make it look pretty, and they should, what should they do? They should mix 1,500 pounds of bluegrass seed with 2,250 pounds of rye and 2,250 pounds of, what was the third one? Bermuda. To minimize cost at $825. And that brings us to the end. Okay? All right. So what we did in chapter 4, and that's all we're going to do in chapter 4, is we worked on slightly more complicated linear programming problems where we couldn't do them graphically. Now, every example that I've done was just a 3-variable example, but there's nothing about the process, there's nothing about the approach that limits you to 3 variables. We could have 4 and 5 and 6 and 7 variable problems and they would work just fine. It's just a matter of writing the inequalities, finding the objective function, putting it all in the system, and then letting the computer do the work. All right, have fun with the homework. If you have any questions, please reach out. Moving on next, we'll move into probability in chapter 7.